this video, we're going to calculate the block shear strength of a channel member. And the question that has been given to us is that a channel C7 into 9.8 tension member is connected to a gusset plate as shown in figure. The tension member is made from A36 steel. We have to calculate the available block shear strength of the tension member for both LRFD and ASD. First, we will determine the properties of the channel section. From Stein manual, we can find out that for C7 into 9.8, thickness of web is equal to 0.210 inch. Total depth of channel section is equal to 7 inch. Diameter of bolts is given in the question 3 by 8 inch. Diameter of bolt hole is equal to diameter of bolt plus 1 by 8 inch. The properties of A36 steel are given. Yield strength is equal to 36 ksi and ultimate strength is equal to 58 ksi. In block shear failure, a block or segment at the end of the member tears out. This represents the block failure for the channel section. In step first, we will calculate the shear area along the shear surface. Shear failure occurs along the longitudinal surface and tension failure occurs along the transverse surface. We can find that the gross shear area is equal to thickness of web into length of shear surface into 2, as there are two shear surfaces, 1 and 2. Thickness is equal to 0.210 inch. Length of shear surface is equal to 3 plus 3 plus 1.5 inch. Putting values, we get the gross shear area along the shear surface. We can see that there are 2.5 bolt holes along the shear surface, that is 1, 2 and 0.5. The net shear area is equal to thickness of web, length of shear surface minus number of bolt holes into dia of bolt hole into 2. Putting values, we get the net shear area along the shear surface. In step 2, we will calculate the tension area along the tension surface. And for the tension area, we need the depth between the bolt holes. And the depth between bolt holes is equal to total depth minus 2 times the edge distance. That is total depth 7 minus 2 inch minus 2 inch gives 3 inch, represents the depth between the bolt holes. In tension area, there occurs one bolt hole along the tension surface, that is 0.5, and 0.5 is equal to one bolt hole occurs along the tension surface. The net tension area is equal to thickness of web, depth between bolt holes minus number of bolt holes along the tension surface into dia of bolt hole. Putting values, we get the net tension area along the tension surface. In step 3, the nominal block shear strength of the tension member is calculated, and the formula for the nominal block shear strength is equal to 0.6 Fu A and V plus UBS Fu into A and T. Putting values, we get the nominal block shear strength for the tension member. If the tension is uniform along the surface, the value of UBS is equal to 1 in the given equation. We have to check the upper limit of the block shear strength, and the upper limit of the nominal block shear strength is equal to 0.6 into yield strength into gross shear area plus UBS into ultimate strength into net tension area. Putting values, we get the upper limit of the block shear strength. We have to take the lesser of the above two values, which will give us the nominal block shear strength. We said that the 93.92 kips is lesser of the above two, so this represents the nominal block shear strength of the channel member. The design block shear strength for LRFD is equal to phi into nominal block shear strength. The phi value for LRFD is equal to 0.75. Putting values, we get the design block shear strength, and the allowable block shear strength of the connection is nominal block shear strength divided by the safety factor. Putting values, we get the nominal allowable block shear strength of the connection for ASD. Hope you guys liked the video, and if you like the video, please subscribe to my channel and share this video with your friends so that they can learn too. Thanks.